Hello, everyone. We are the FIU team in the Solar District Cup. We were assigned the Ball State University case. And this is our team comprised of students from 4 different departments, which were split into 6 different sub-teams shown here. And we would like to take a quick second to thank and acknowledge all of the faculty advisors and graduate students that have helped us along the way. So now moving forward. From our analysis of the BSU site, there are several benefits and constraints to consider when designing a PV system. Under the zoning code for Delaware County, rezoning would not be necessary for a proposed design. BSU has plenty of flat area that can be used to meet the university's energy demand, and it owns most of this land that we will use. There will be no land acquisition costs for the majority of this project. However, there are some constraints that need to be considered while designing the system. Solar irradiance in Indiana is not ideal, so the production from solar panels would not be as high as it would be in other parts of the country. The USDA Web Soil Survey also points out that the soil types present in the land used for the ground-mounted system are not well suited for installing PV. Our design places panels on a parking lot controlled by a local church, and negotiating a land use agreement may present several obstacles if the system was to be built. Lastly, construction will need to be carefully planned out in order to not interrupt the busy university campus. In order to address these constraints, we recommend 2 actions. The first is having a stakeholder plan where a project liaison is put in place to address concerns from BSU, its student body, Delaware County, and the local church, which are all groups that can influence the success of a project. Our design considers the university master plan, ensuring that no panels are placed on a building that may be demolished or replaced in the future. For example, our design originally planned to place panels above the Emmons garage. However, the university released plans to begin demolition in 2020, and our design was changed accordingly. We also plan to keep the public involved and informed with the community engagement initiative. And in order to prevent any permitting issues with the county, we've compiled a list of necessary permits, but we also recommend working with local consultants from an early stage. The project liaison will also serve as an intermediary between the church and BSU in the early stages of the project to negotiate the land use agreement. Before any construction begins, we strongly recommend thoroughly surveying the land use for the ground-mounted system. Soft soil makes it difficult to secure mounts to the ground, and frost conditions lead to frost heaving, which can both damage the solar panels. If the wrong type of mount is chosen, panels may fall over or break. Our team recommends helical piles to secure the panels to the ground, but conducting an independent ground survey will be crucial in order to determine if using this land is possible for this purpose. So for our construction timeline, we used a goal of 8 man-hours per installed kilowatt. And we chose to begin construction on December 9th. We chose this date because it is the day after the semester ends, allowing workers to take advantage of reduced campus traffic for the first month of construction. And now Myra with the conceptual design.
Hi, within the area available on the campus, our PV system uses the rooftop areas of 11 buildings, the parking lot by the church, and the available land to have a total sizing of 15.4 megawatts. We selected inverters according to their capacity and DC inputs. Our design includes 333 inverters of 4 different brands. We use 10 kilowatts inverters for the designs with less energy output, 60 kilowatts inverter for the ones that generate the largest power, and one 3,000 kilowatt for the battery. The following equipment was selected according to its most important characteristics: capacity, efficiency, and cost. Sun-powered solar panels are the most efficient in the market. The 470-watt monocrystalline panel was selected in order to maximize the power generated in each design. We also selected 4 types of transformers of 2 different manufacturers, and we used 4 batteries. To optimize the annual energy output in each design, the 2 angles of the panels were changed. We now use angles from 17 to 35, and depending on each angle, a different row space was used to decrease the shading between panels. In our initial design, only 1 model of inverter was considered. To optimize each design, the number of inverters was reduced more than 20% by using different types of inverters according to their capacity. Consequently, the total cost of the equipment was reduced. The ground-mounted system is the one that generates more power. We made changes in row spacing, tilt angle, and number of panels to comply with the regulation and reduce the shading losses. And due to this change, it was possible to decrease the numbers of inverters. We leave you with Carla with the architecture building.
Thank you, Mayra. For the challenge of the installation of solar panels in the 55-degree slope wall of the architecture building, we propose a layout of 80 solar panels to be integrated on the building's glass. It includes horizontal spaces of 5.35 feet between each mount for operations and maintenance processes. To comply with the university's vision, the panels will be placed only on the right side of the building, leaving the space in which the staircases are completely available for visibility and views. The mounted panels were given an optimal tilt angle of 17 degrees with respect to the glass wall to produce an annual energy of approximating 200 megawatt hours in combinations with the ones mounted on the rooftop. It is recommended to install a set of 8 retrofitted top of pole mounts by welding them into horizontally spanning rectangular beams. We did static analysis on these beams, and they proved to be supportive of the whole entire system. Additionally, we are going to propose the implementation of shaded solar-powered benches in bus stop areas and recreational tables with integrated solar panels all around campus. Ultimately, this proposal aims to satisfy BSU's current goal of achieving climate neutrality and increasing community engagement. Now I'm going to leave you with Samantha.
To model the PV impact on the grid, we use OpenDSS. We receive the outputs of the panels and inverters from Aurora and use a transformer to step up the voltage output of the inverters to match the voltage of the grid. For the PV installation, we modified the current model with the university loads and added the PV system for each of the 11 buildings. Lastly, we added the ground mountain since this has the higher power output and also is located farther away from the university. We created a new line that has enough low capacity to hold this power. The battery was located near to the substation at the point of common coupling between the ground mounted, the substation, and the university loads. This was selected based on accessibility and aesthetics. For the grid optimization, we developed an algorithm in MATLAB that receives the inputs shown in the left, including Aurora's, then connects to OpenDSS master and starts placing all the PV systems automatically. The transformer selection, the PV siting, and the inverter control were our main focus of optimization. For transformer selection, we focus on reducing the cost. For PV siting, we developed an iterative algorithm for the ground-mounted connection to the grid. The algorithm test all the scenarios, check all the ones that do not have any voltage violation and overloads, and the final selection is based on the shortest length. We decided to use inverter control to reduce the maximum voltage of the system and also to avoid damaging the equipment due to unexpected voltage peaks. For the inverter control, we tested 3 different ballpark curves. All of them were tested in the ground-mounted system, and the first one is the one that showed the greatest reduction in maximum voltage. This curve was tested in 3 different cases, and the last one is the most beneficial for us with the reduction in voltage and is installed in the ground mounted and in most of the buildings. This is the impact of our PV system on the substation. This graph starts at 8 p.m. We can see how after 6 a.m., the substation does not need to provide any power to the university. However, before this time, the substation is still providing the same power. That's the reason why we decided to use batteries. The battery was placed near to the substation for aesthetics, accessibility, to avoid danger, and also to reduce power losses. The sizing of the battery, we use a power rated based on the 75% of the maximum power consumption during a year. For the power capacity, we selected 9 megawatt hours that are able to supply up to 3 continuous hours at the power rated. For the charge and discharge curve, we use re-opt. In the re-opt, we tested different scenarios. The first one is without battery, and we can see the excess in the PV production. The second one with a small battery, and the last one with a high capacity battery. This battery and this ballpark curve ensure 3 hours of power during outage, and is based on resilience. This charge and discharge curve shown was tested on OpenDSS and compared with the battery trigger controller from OpenDSS. Here we can see how the charge and discharge curve charges even more the battery and also discharge at the times where no sunlight is present. This is our final design. It doesn't have any negative impact on the grid, and also any of the components exceed our voltage limits. Our final offset is a 93.25% for a PV plus storage system. Thank you, and now Juan starts with the financial analysis.
Our financial analysis can be divided into 3 sections: inputs and research, softwares and analysis tools, results and comparisons. Our most important inputs were the utility rate and the tax incentives. We used REOP Lite, SAM, and the solar MBA model provided by the competition to obtain a power purchase agreement, PV versus utility scenarios, and an investment assessment. From the table on top, an energy price of 7 cents per kilowatt hour was calculated using the utility charge per kilowatt hour and the demand charge. For the tax incentives in the tax details table, we used both the makers and ITC, but to be able to use the ITC at 30%, we had to come to an agreement with the development plan team to begin construction in 2019. When comparing the cost of the system of the progress and final deliverable packages, there was a reduction in the total sales price of 62% due to better pricing of the modules and the optimization of inverters, transformers, and labor costs, even though there was an additional cost of $3 million for storage. The amount of production that was obtained by the quantity of panels, their production capacity, and the amount of sun hours per day at the location. With this system, we were able to obtain a yearly output of 16.2 megawatt hours, meaning there was a reduction of 2.5% in production because of the implementation of regulations required for the ground-mounted system. Before we implemented the batteries, we tried to run REOP Lite, but when doing so, it showed us that PV system was not required for this location due to its low utility prices, which meant that REOP could only be used for resilience purposes and to obtain the charge and discharge data based on the system design. The system advisory model was used to verify the financial analysis MBA model and to obtain the inputs of P50 and P95 kilowatt per year production, which were required for the MBA model to run. As shown in the project debt table, we decided not to have any project debt and just have equity investors for the cost of the system because it was what gave us a positive cash flow. After that decision was made, the partnership flip was ran using a PPA price of 3 cents below the utility price while having an escalator rate the same as inflation until no further improvements were obtained. At this point, the PPA price was raised to be the same as the utility charge per kilowatt hour, but with a more aggressive escalator rate of 3.2%. By doing this, we were able to maintain a positive cash flow and make the investors obtain a combined net present value of more than $300,000, which could be used to implement the solar tables for the community involvement. We generated savings for the university throughout the 20-year period for a total of savings of $25 million. This was accomplished by keeping the PPA price below the utility price for the 20-year period. These are references. And as for a system, we made a system that is viable for the university and its investors, a site plan that uses most of the area available, structure and grid integration for the architecture building, and an optimized grid distribution by reducing the voltage violations, implementing batteries, and lowering the number of inverters. We thank you all, and now we welcome your questions.